And the first thing is a little correction from yesterday's class. Well, somebody brought it up when we were calculating a bias current. You remember when I was calculating a resistor value that I had instead of 10 milliamps, I had 100 milliamps. So on yesterday's handout, if you were to go to slide 18 and just make a note for yourself, for resistor R3, instead of 68 ohms, it is supposed to be 486 ohms, 486 ohms. All right? So let's put that down so you have the correct thing. After today's class, after today, I'll upload the correct version just in case. Okay, so today we will continue and conclude our the topic on regulated power supplies. So far we've dealt with our regulation. We've dealt with rectification. So we started off that early on, and then we dealt with the simple filter, and then we started to look at how to regulate, and we went through, we used the Zener diode, and then we boosted the current capability of the Zener diode by adding the pass transistor. And then we started to get a little more control on it. The pass transistor worked well, but as we saw yesterday, there are changes to VBE. And because of that, in the transistor, when it's working, the characteristic varies so that there's a chance that the output voltage of the regulator will fluctuate over time. So to isolate the output voltage from the variation in that pass transistor, we introduced something called a feedback voltage regulator, the series feedback voltage regulator, where we added an additional transistor to it. But basically, the block diagram for the series feedback transistor was that in the middle of everything, in the middle of the circuit that we had, we put in this error amplifier. And the error amplifier, the first version, or the version that we spent some time discussing yesterday, was created using a single transistor. One input of the transistor goes onto the transistor's emitter, which is the reference voltage. The other input goes into the transistor's base. And the output of the transistor, the collector, the voltage of that fluctuates depending on what happens with our regulated output voltage. So as it went up and down, the error amplifier gave the opposite reaction. So the voltage output Vout tried to increase, the error amplifier decreased the bias on the series element and decreased the voltage out. And if the voltage output went down, the error amplifier increased the supply, the voltage bias on the pass transistor, so that the output voltage tried to climb back up. So the net result was that everything stayed fairly stable within the design limits of the power supply. You are designing it. Always remember there's a current limit that the design is trying to satisfy. So it will work for that. It will not work beyond that. Okay? And then we ended yesterday by saying, but wait a minute, one of the devices that works well for this sort of error amplification, where it's taking two signals and subtracting one from the other, is in fact the operational amplifier. It has an inverting and a non-inverting input, and depending on what values you put, it finds a difference between the voltage on the inverting and the non-inverting inputs. So we said, okay, let's, instead of using the transistor now, we're going to replace this error voltage amplifier by an operational amplifier. Now notice how we've wired it up here now. So we have the op-amp in place, and the non-inverting input of the op-amp, circled in blue, is where we are going to connect our reference voltage, which is from that Zener diode. The measured voltage, which is the one that we detect using the voltage divider comprising R1 and R2, we send to the inverting input of the amplifier, and then the output of the amplifier is driving the base of the pass transistor there. Right? Notice that the transistor is operating as a non-inverting amplifier. All right. So because of that, we are able to power it from the, we can use single-ended operation here. Right, we don't expect a negative voltage coming out, so we can supply the power supply to the op amp. As you see the connections there, I'll put this here. One is on ground and one we have connected to the positive supply. And one of the things why this is going to work for us is because of the virtual earth behavior of the operational amplifier. Remember what the operational amplifier tries to do is that if you put a voltage on, for instance, a non-inverting input as we have here, which is connected directly to ground, right? So we put a voltage here. The virtual earth behavior means that the other input, in this case the inverting input, tries to equalize to become VZ. So we have VZ on the positive input of the op amp. The virtual earth behavior of the op amp tries to make the inverting input equal to VZ. You would remember that from operational amplifier behavior and the sort of circuitry inside. I don't know if you were ever shown the inside circuitry or discussed it in any way, like transistor differential amplifiers, for instance, and things like current mirrors. You ever heard that term before? Okay. All right. So maybe if we have some time later on in the course, I'll probably put up that. Okay, you didn't go into it. The current mirror is just a way to make an amplifier, make one input mirror, or the current flow in one input mirror the current flow in another transistor that are working together, right? Anyway, irrespective of that and not necessary to know, but you would have heard this thing, the virtual earth behavior, right, of the op amp. And it basically is created because the op amp has an extremely high open loop gain. When you don't connect anything to it, you remember the op amp has gains of the order of 10 to 5, 10 to the power 6 and the like. So if you just look at the circuit right here, if we put VZ on the non-inverting input and the inverting input is trying to track that, so because of that virtual earth behavior, that point circled in red now is VZ, then that allows us to calculate the relationship between V out and VZ, right? And V out is simply VZ into 1 plus R1 over R2, okay? You work out that the usual way that you would have calculated or derived the gain for non-inverting operation. Okay, so we have a simple expression right there. And let's ask some questions. So some observations here, right? First off, I am supplying the op amp from the unregulated supply. Now, why do you think I'm doing that? Because the unregulated supply, remember, could fluctuate. It goes, it has a ripple, it has a maximum and a minimum. The regulated supply is nice and level. But why am I choosing to supply the op amp from the unregulated supply? Okay, Aidan, so you're saying to give the full amount of voltage, meaning what? When you say to give the full amount of voltage, to give the access to the full amount of voltage possible, exactly what are you talking about? No, you're on the right track, but I want to make sure. No. Voltage is correct. You are correct. No, not the voltage. You are correct, but why? Okay, let me help you out. The op amp needs to vary between two levels, exactly. So if I supply an op amp from, let's say, in this case, let's say I'm putting a 15-volt supply on the op amp, okay? What is the maximum voltage output that I could typically get from the op amp? If you remember your op amp discussions. Anyone remember? Okay, so the answer is less than 15 volts. What happens is that the op amp has an upper and a lower limit. If you're operating at plus and minus, the normal bipolar supplies, if you supply it at 15 volts, depending on the op amp, it will usually get between 1 and 2 volts maximum of the power supply. It can't get exactly equal to the power supply. There are some specialized operational amplifiers that may be able to do that, but they're expensive, and there's a reason for that. But generally, the normal sort of op amp like you would have met, like the 741, you normally get within about 2 volts of the supply. So if I decided to power the operational amplifier from V out, and V out was a nice 12-volt supply, it means that the maximum voltage swing I could get out here is probably just going to be plus or minus 10 volts. Or in this case, if I'm supplying it from a single-ended volt supply, then the maximum output I'm going to be able to get here is just going to be plus 10 volts. I'm trying to regulate 12. So I need the op amp to get as close to 12 as possible, right? Less, remember, the only difference between here and here is here. Right, so we have 0.7 volts. So the op amp has to be at least 0.7 volts higher than the output here. And if the highest I could get is 10 volts with a 12-volt supply, is not going to work. Okay? So that's the first reason. So we supply it from the unregulated supply. The op amp typically takes very little bias current, so that the load on the power supply, on the unregulated power supply, by supplying this is going to be minimal. Okay, so question number 2, I am supplying the Zener diode also from the unregulated supply. Why? Anybody? Actually, that was a trick question. There's no good reason why I should. Okay, yeah, I was asking Aidan, why am I supplying the Zener from the unregulated supply? Right? And the answer is no good reason. This was a little bit of a trick question. In fact, the Zener could be supplied from the regulated supply. Right? There's no reason to. And in fact, the better design, which I have drawn later on, is to really supply the Zener diode from the regulated supply. It gives us a better, more stable design. Remember, from our design yesterday, you calculate this value based on the worst case performance of, yeah, well, so sometimes it's good to think and then realize, wait a minute, stretch your brains. So V unregulated, once you supply the Zener from the unregulated supply, you have to cater for the worst case in the unregulated supply. As we saw yesterday with our 1-volt ripple and our 15-volt AC supply, that was something like 20 volts. So it was going between 20 and 21. You have to cater for that. Whereas if you supply the Zener from the regulated supply, that's very stable. The Zener diode is considerably less than the regulated output supply, so that you don't have to worry about it dropping out of regulation and what do you call it, stopping its regulation function or switching off or being driven into over voltage and over current and the like. All right. So the better design really is to bias it there, and I'll bring up that circuit in a little while. So how do we design here? This one is very simple. Again, you start off, go here. So let's repeat the example from yesterday. So using the same thing, 12 volts at 1 amp, that is what I want out. The regulator is coming from a 15 volt supply, and the transistor again has a gain of 100. So everything that we did yesterday, the first thing, of course, that you do is that you calculate the value for the Zener resistor. As we did yesterday, the same voltage here is going at 20 volts worst case at maximum load, 21 volts at minimum. So you calculate the value here. Of course, you choose the value of the Zener. I think we chose a 7 volt Zener diode yesterday. So you choose the value of the Zener diode. You look at the bias current for it. So you go back to your data sheet. The bias current I think we chose was 5 milliamps, and you could calculate R from that. The next thing you do is these two things here, right? So if I have 7 volts at this point here, the calculation now is to give me 7 volts here. So here's 7 and here's 12. Okay? So I'm now, what I could do now, remember I have this equation from before. Go back here. So plug this in. I know this value is 7. I know this value is 12. Yeah? So what I could do now is I could get out of that, I could now get a ratio of R1 to R2. Right? I don't have a value as yet, but I could get now that R1 and R2 is equal to something. If I was to plug in the values that I had inside of there for the particular problem that we have here, I could get that R1 over R2 is equal to, the ratio of that is 5 to 7. And the choice now is as simple as picking a value for one of them and then calculating the other. Bearing in mind that these resistors here are taking current from the power supply as well. Remember, the power supply is designed as a 1 amp 12 volt supply, but there's 1 amp you want to supply usefully. So you want as little current as possible coming, being diverted elsewhere. So R1 and R2, you're free to choose fairly big resistors for that. The op-amp, if you remember, the op-amp actually takes very little current to work. So that the current going into the op-amp here is going to be very small. So with that in mind, you just simply choose a value. So if the ratio is 5 to 7, right, that is R1 to R2, I could pick out, let's pick one. So let's call this 100K, right? If I pick R2 is 100K, then R1 is simply going to be 5/7 of that, whatever is the sort of closest resistor value I could get. All right, or the other way wrong, if I picked, if instead I pick this one as 100K, then the ratio is 5 over 7, then this one will come out to be 140K. Right, so you see that the current going through that will be 12 volts over 240K, which is a very small amount. And then the transistor remains the same. So the transistor, as we said, requires a base current of 10 milliamps. The only thing you have to watch out is that if the op-amp here can supply this base current. Remember, how we're regulating it is by sending this voltage up and down as normal. So if the voltage tries to, if Vout tries to go up, then it will try to change this voltage here, but that voltage must be equal to the Zener voltage. So regardless of what Vout is attempting to do, the virtual earth behavior fixes here at whatever the Zener value is. right? And by the gain of this circuit now, because we calculated R1 and R2 according to this equation here, this is fixed. We have calculated these values. So regardless of what the output is trying to do, it is constrained. None of these things can change. VZ is fixed, R1 is fixed, and R2 is fixed. So regardless of what that pass transistor tries to do, that output is going to remain at whatever you designed it to be. The only problem, as I said, is if you have a pass transistor here and you are attempting that the base current for this, which in our case is 10 milliamps, if the base current is more than the op-amp can supply, then the circuit wouldn't work. All right, and you have to check your specs. A typical 741 can typically supply about 100 milliamps. Right, so it will work quite well for this sort of situation. If, however, the op-amp can't supply the base current to the pass transistor, what's one other alternative that you can use? Instead of a pass transistor, a single transistor, what is a possible configuration that you can use? Something that you met before. Came across something called right, you remember something called a Darlington pair? Remember that? So the Darlington pair basically works two transistors, one feeding the next, right? So it will be the configuration. You just go back to your little notes. So what you have, and you have the other transistor. Very bad drawing, but there you have it. So you have one transistor supplying the current at the base of the other transistor. So this will be the power transistor. This is a smaller transistor in there, and that the net gain of this thing, remember, is HFE1 multiplied by HFE2. So a much higher current gain, meaning that the current required here is a lot less than in the single transistor version. Okay, and their Darlington transistors can also take a very large amount of power. Remember, we said that, and we'll talk about it further on, that the transistor here, if this is 12 volts and this is 20 at the highest, and you're carrying 1 amp, the transistor has to dissipate something like 8 watts at full load. All right? That was in the discussion yesterday. So any questions on the using the op-amp in this configuration? Anything that's not making sense? All right. So good so far, until the exam question comes. So notice the variation. This is version 2.0. So here I now have the op-amp still supplied from the unregulated supply for the reasons that we said, but here I have the Zener supplied from the regulated side now. So here we don't have to worry about the fluctuations in the supply to the Zener. The Zener voltage here, if we're using the example from before, the voltage the voltage here is going to be 12, nice and regulated. So if this is taking 5 milliamps, and we still have our 7 volt diode here, right? We can now calculate the value of R, and the diode is nice and well protected because the voltage is 12 volts, is not going to go anywhere within reason. All right, so this is usually the preferred way of designing a circuit. Okay. Right. So that is the last slides yesterday, and what we've done now are how you design a regulated power supply using discrete components. And there are advantages to doing it, there are disadvantages to doing it. One of the advantages is that you can basically design it to give you any sort of voltage and current that you want. But more or less for a lot of sort of applications, the alternative to using it, and the sort of simple, relatively speaking, way to create a power supply to use to power whatever circuit application you're designing is to use an integrated circuit regulator. First off, all of the circuitry that we just discussed are actually inside of many of them. And then they give you, in addition to that, they have the reference voltage, the error amplifier, the series pass device, and then they add something called overload protection, which we'll talk in the second half of today's class. And then they come in three basic formats, which are fixed positive, fixed negative, and of course the ones that you can adjust the output DC to what you want. And the simplest of them just have three terminals. The three terminals there's an input, there's an output, and a ground. And you can't get more simple than that. Right? The unregulated supply goes to the input terminal, and the regulated output is available at the output. You ground it to the third terminal properly. And if you look at the sort of the figures here, right? These things come in a variety of cases. Remember yesterday I mentioned this one to you, the TO220. This is the one where there's a metal tab on the back of the circuit that you have to attach to a heatsink, because presumably this is going, if you were to make the 1 amp circuit that we spoke about, the 1 amp power supply, this too is going to have to dissipate the 8 watts, because you're putting in the same unregulated voltage out, you're getting the same regulated voltage coming on the other side, and it's carrying the same current. So this has to dissipate 8 watts. They make it in a way that you can mount it. This one here is what is called a surface mounted device, SMD. Right, so this thing here would be very small, probably about maybe a couple of millimeters square. Again, it has a heatsink on it, right on the back, and the back of this entire thing is metal, but it's mounted flat on the circuit board. And what they do is on that area, on the other side of where it's mounted, you have a big wide area of copper to dissipate the heat. So it's the same process. Okay, let me get back down to here. Right, and you have all sorts of options here. Both positive and negative voltage devices are available. Right, I'll leave that for a little while. So this is one that we look at, which is the 78XX series of positive terminal regulators. The case is like I showed you there. It's a case. The type of case is called a TO220. All right, it has everything that we spoke about before. On top of that, it has internal current limiting. So this particular one, the 7812, can supply 12 volts at 1 amp, just like our design circuit inside of there. It will limit the current to a little over 1 amp. If it gets too hot, so for instance, if for some reason you forgot to put it on a proper heat sink, it has a temperature sensor inside that will cause it to shut down. Right? It has a short circuit protection that will prevent it from overheating and shutting down as well. So essentially, for most practical purposes, it is indestructible. It's the kind of thing that they make power supplies for labs and for students, as we were joking about yesterday. And provided you heat sink it adequately, they can deliver over 1 amp. It will deliver over the 1 amp output current at the 12 volts. If you don't, it will overheat itself and shut down without damaging. All right, the way you damage this thing is to put the wrong polarity voltage on it. So instead of putting, which I'll pull up here, right? So this is how we operate it. So the way you damage this is by putting the wrong voltage here, the wrong polarity. So instead of putting the plus unregulated, there, you put a negative voltage here. You're going to damage the device. Some of them even have polarity protection inside. So it is as simple as this. You get the LM, whatever series it is. The handout that I put up on the web on the course page has all of the family members for this series. So you can get from low, which is down at the close to 3 volts, all the way up to in the 20s. And to wire it up, you simply put it there. You hook up the input to the unreg and the output, and they put these little capacitors here just to filter out what they call transient noise. Right? There are always little, because once you have a circuit board and you're in the air, for instance, wherever you're sitting down now, you have 60 hertz electromagnetic radiation present because of the 60 hertz power supply in the wall outlet close to you. Okay, you also have a lot of noise on the power supply, on the power line, because of the type of power supply that your laptop, for instance, may be using. So to sort of clean out all of those things and to make the regulator perform a little bit better, they have these two small capacitors, one at the input, which is 0.33 microfarads, and the other one is 0.1 microfarad. They're small, so they're really designed to get rid of high frequency components, right? You remember that the reactance of a capacitor drops as the frequency goes up. So at DC, the capacitance is, those two values are basically open circuit. But as high frequencies, they start to become more and more conducting to high frequency components. So they basically shunt the high frequency components to ground and let the low frequency and the DC components pass. Yeah? So real straightforward operation. This is what it looks like inside. Notice that it has many of the things in our discrete, what do you call it, in our discrete discussion. It has a series pass element, it has the error amplifier, it has a reference voltage. Okay, the reference voltage, instead of using a resistor, it has a current source that supplies a very constant voltage, a very constant current, sorry, to the reference voltage, so it's very stable. The starting circuit here is just to prevent, when you switch it on, when you go from 0 to 1 here, right, like a step response, those of you doing signals with me, that the output goes 0 to whatever the design is. It doesn't do this and then settle down, right? It doesn't go beyond and above and so on. So the starting circuit prevents that. It basically slows the startup. And then on board, you have thermal protection, which is a temperature sensor, and it's connected there, so it will shut down the supply. It will shut down the series pass element if anything happens. And then you have some other protection around it for like short circuit and overcurrent protection as well. Yeah. So everything that we spoke about, and before today is done, we're going to talk about the overcurrent protection as well. Right, so here, again, and now we're in a position, because you understand how some of these things work, to look at a circuit like this. This is an interesting application. They call it a tracking voltage regulator. Right, now notice how it's supplied. Right, we have two outputs. So we have to supply a negative unregulated, sorry, a positive unregulated here and a negative unregulated here. Okay, this is our what do you call it, the three-terminal regulator that we just spoke about. At the point in time when you start off the circuit, this negative voltage is 0. This goes to plus, let's say plus 12, all right, if we use the 7812 device. So this point here, if this is 0 and this point here is 12, here is going to be, because these two resistors are exactly the same, here is going to be at 6 volts. Here, let me get a pen. Here is going to be at 6 volts. So if this point is at 6 volts, it is going to try and you remember the other terminal of the op amp is at 0. It wants to make here 0. So the only way it can make this point 0, when we started off as at 6, the only way we can make this point 0 is for the op amp to drive this pass transistor and make this point minus 12. Once this becomes minus 12, then this point here goes to 0, because I have plus 12, minus 12, and 2 equal resistors. So what happens now is that if this changes in any way, in order to keep here 0, this op amp forces this side to do the opposite. In other words, it's tracking. Right? So this is one way to get an identical, like a bipolar supply for a lab. So you design it, and you design the positive, you use the positive regulator as the control, and whatever you have on the positive, the circuit is going to make the negative track that all the time. And whatever fluctuation happens on the positive side is going to be reflected in the negative side of the circuit. Yeah? Now this is the kind of thing, as you go through the course, I will like that you're able to, for instance, if you have a circuit like this, not necessarily maybe as a tutorial question, but for your own reading, that you're now able at the end of what we do here in electronics too, that if you meet a circuit like this for some sort of application that you're looking at, that you can understand how it operates. Right? Remember, and it's very simple principles that you have to remember. You have to remember, in this case, how an op amp works. Okay? What causes the transistor to work on some simple Ohm's law and circuit theory here. What voltage dividers do and the like, and just follow the operation, what you know the operation of the device to be. Yeah? Fair enough? And then, if you want, this now allows us to make, very good. So this one now allows us to make a variable volt supply. And the variable volt supply is taking an input and using a 7805, that will be a plus 5 volt regulator. Look at the last 2 digits there in this family. And now you see that because of the gain of the amplifier, that and you check the spec sheets to see, the output is whatever the input is, 1 plus R1 over R2. Now, what we have here is we have a variable resistor here. Now, notice what is happening here. When depending on where I put the wiper, they will call one part of that R1 and the other part R2. Okay? So instead of having a actual potential divider, they're using one variable resistor, and depending on where you position the wiper of the variable resistor, one part of it will be R1 and the other part will be R2. So you can vary the ratio of R1 to R2 by moving the device all the way up and all the way down, right? Again, it cannot go to 0 because the op amp has to be, even if it's powered here, these devices need a certain potential difference between the input and output. So you will never get it regulating all the way down to 0. Okay? It needs some voltage to be able to operate. But again, if you check the handout, you'll be able to decipher why they give it that rating 7 to 30 and fiddle with some values. Look at the equation, the output equation, and you will see they will explain that. So back to our original op-amp design now, right? Forget the 3-terminal for the time being. If I were to ask you how to make this a variable voltage output, how to get a variable voltage output from that, what would you do? Don't go all comatose on me. What do you think? How can I make this? And if you have this slide, if you go back, let me just go back here a little bit. Yeah, vary R1 and R2. Yeah, you can, but I want it variable, right? So let's go back to here. Right, so I want to make this give me a variable output. So instead of fixed, I want to make it variable. As you said, vary R1 and R2. But you don't really have to vary both of them. All you have to do is to, right, you change either thing, or all you have to do is to change one of them. So if you make R2, for instance, variable, then depending, now I don't like particularly like that one, but if you make it variable, depending on the value here, the output is 1 plus R1 over R2. So if R2 changes, then I could get it from very low to very high, depending on the value of R2. The part I don't like about doing that is that if R2, if you put a variable resistor and then you make the value 0, then you have something, you have a 0 in the denominator here, which is not a good idea. So the better way might be to make R1 variable, right? So if R1 is variable, when R1 is 0, I get that the output is VZ. So in this case, we pick 7 volts. And if R1 is, let's say we vary it such that R1 to R2 might be, let's say 3, right? Then I could get VZ going, if R1 to R2 is 3, then VZ is 7. Then in theory, I could get V out as 28. What am I doing here? Get back my pen. Right. So if I make R1 variable, when R1 is 0, I get VZ, which is 7. If I make R1 3 times as big as R2, then I could get, in theory, up to 28 volts. But of course, my unregulated supply here is only 20 for the one that I use. So I could get all the way up to, well, within a couple volts or 20. But certainly I could get from 7. Yeah? So that gives you an idea of this sort of range. The other approach that sometimes is taken is to leave these two fixed here and to insert a variable resistor in here. Okay, so this gives you a little more tolerance over it. It would never go down. You remember, if this whole chain, if for some whole reason this part R1 over R2 goes to 0, then the lowest value you could get out of this supply is whatever the Zener diode value is here, right? So in our case, for this, the lowest value Zeners you probably get is like 1.2 volts. So if I were to do that, I could get the Zener diode going from 1.2 volts up to some sort of maximum, whatever my supply is. Sometimes people put the variable resistor here between these two, so that there's no chance of accidentally, even if the resistor is 0, okay, you don't have a 0 appearing anywhere in the output circuit. You don't want to have very low resistances appearing there, right? It's sort of protected, but it works within a range. Yeah. So that's one easy way. So you know how to take the basic one that we had and convert it now into a variable voltage. And we sort of partially answered the question in the previous slide why the output voltage will vary, but it's not going to go from 0, right? It will never get to 0. Not with this sort of configuration. Yeah? So you could put a variable resistor here, and you can change this to a very small value so that you could get from a fairly small value up to whatever your unregulated DC supply can provide to you. And one other advantage of this is that, let's say I have an application where I need something like 100 volts DC at maybe 100 milliamps. Okay, the integrated circuit regulators like these, you're not going to get any of these that is going to give you a regulated value of 100 volts. If you need that kind of thing, you have to design it from scratch, and you now know how to do that, right? Whatever value you pick for the Zener diode, these two resistors plus the value of the Zener diode and the gain of the op-amp will give you this. You design for the 100 volts. Of course, you now have to make sure that you have a transformer that could give you at least, but the transistor here, you need at least about 103 volts, 102, 103 volts DC at the worst case coming out of that. So you have to go back and get the transformer and the filter capacitor and so on. All right, but if you have to design, and there are cases like that, there are motor control circuits and so on that work with high voltage DC. All right, so let me see a current source. What's the question? Just now, let me put it back up on the chart here. Okay, so a current source is using an IC instead of a Zener because the Zener forces a mini, which is preferred. No, not quite. Just look at the circuit that we have here. We are biasing the Zener with a resistor. Okay, resistors carry current and therefore they get slightly warm so that the value changes. This is always a R plus or minus some tolerance, right? You remember that color band on the resistor? The resistor has a tolerance, meaning that when I calculate that, it actually could vary anywhere, in this case, plus or minus 5%, plus or minus 10%, or as it gets warm, the value changes. If the value changes, the value through the Zener current, or the value of the current through the Zener also changes. And because of that, the Zener voltage, remember, the Zener characteristic is supposed to, just now I'm getting some behavior here, is supposed to do this. That variation there happens, it is not perfect. There's a little bit of variation and it depends on the current through the Zener. So one way to insulate that, instead of supplying the Zener with a resistor, we supply the Zener with a fixed current, a constant current, right? And that's where the constant current supplies come in. So that's what they do inside of here, right? Inside of here, this current generator that they're talking about here, right, is really supplying a very constant, unchanging current to the reference voltage. So the reference voltage remains absolutely stable. Okay, there's a lot of circuitry that goes in that. And when you check the handout, if you go and go back to the manufacturer of the device and look, it's an interesting exercise when for homework or for your own interest, you will actually see how complicated the circuit inside of the IC regulator is. Yeah. So, any questions? Well, I'm sure you have, and you will have more as you think about it, but immediate questions or concerns? All right, so I will stop the recording now and we will take a 5-minute break and then